So the last thing we're going to talk about is solving inequalities with absolute value. So friendly reminder that if I have an equation with an absolute value, right, I have that x equals 4 or x equals -4. And this is because with an inequality, there are two possible values that I could substitute in to get an absolute value of +4. Friendly reminder that absolute value is always positive. So when we're working with inequalities, if we have a be a positive number, because remember, if I had the absolute value of x was less than -4, this would be always true, right? Because the absolute value is always going to, this would have no solutions, right? Because the absolute value is always positive, so this has no solutions. Or if I had the absolute value of x is greater than -4, this would have infinitely many solutions because absolute value is always positive. So that's why our a needs to be positive. So this has -infinity to +infinity solutions. So if I have the absolute value of a, the absolute value of u is less than a, this is equivalent to -a is less than u is less than a, okay? If you are familiar with set theory, this is when we're looking for the intersection of these two equations. We're looking for where they overlap. Now, why is this the case? So let's say I have the absolute value of x is less than 4. Let's take a look at a number line. So what are some values that I could substitute in for my absolute value to be less than 4? Well, I could substitute in, how about a half? I could substitute in 1. I could substitute in -3. All of those values would have an absolute value less than 4. I could even plug in 15/4, right? That's really close to 4. -15/4, right? As long as I don't substitute in 4, right? 4 is not included in this solution set. So my solution would be all the numbers between -4 and 4. Here it is highlighted in green. So this is basically saying I want where -4 is less than x and x is less than 4. And if I was to graph both of these on a number line, oh, this is a really ugly number line. Let's try and make it a little prettier. If I was to graph both of these equations, inequalities, on a number line, my solution set would be where they overlap or where they intersect. So let's say x is greater than -4. We're going to graph that in orange. Let's let red be where x is less than 4. So if we're looking for the intersection, which is and, right, this is where these overlap, okay? So my solution set is from -4 to 4. You can also rewrite this as a 3-part inequality. You could have had -4 is less than x, which is less than 4. So this is when you're working with less than. When you're working with greater than, that's when we use or, okay? That means u is less than -a or u is less than a, okay? This is the union of our solution sets. So why don't we go ahead and open up another window where we can take another example. So if I have, let's switch to a nicer color, the absolute value of x is greater than 4, okay? Let's draw our number line and let's think what are some possible values that I could substitute in and have an absolute value of x greater than 4. Okay, so I could plug in when x is 5, right? Because 5 would have an absolute value greater than 4. I could plug in when x is 7, right? Because absolute value of 7 would be greater than 4. But we also have to remember the other side, the negative side, right? I could plug in -5 because absolute value is always positive. Remember, we're measuring our distance from the origin. I could plug in -5. I could plug in -17/4. That'd be really, really close to -4, right? So my solution set's going to be not including 4 all the way to -infinity, because if I plug in any of these values, I'm going to get a true statement. And if I have to take the positive side as well, because if I plug in any of these positive values that are greater than 4, I'm still going to get a true statement. So here my solution set goes from -infinity, because remember we read from left to right, all the way to 4, -4, union. This is what this symbol stands, union. It means we take both sets together. So we're going to union that with 4 all the way to positive infinity. So it's not really a mnemonic. I was trying to find a way to help us remember when to use intersection or union. So I remember that for greater than, you use union, which is also sometimes represented as or. And for less than, you use intersection, which we call and, right? That's when we're taking these things together. So you can remember these two words, gore, land, right? Because greater is or and less than is and, okay? And here's a picture of gore, because now you can't forget Goreland, right? So why don't we work through a couple examples. I have 9 minus x plus 3 is greater than or equal to 5. And the first thing I'm going to have to do before I can use our theorem is I need to isolate my absolute value. So I get negative x plus 3 is greater than or equal to -4. Then I have to go ahead and divide by a -1, right? Because I've got x. That's what I have, x plus 3 is less than or equal to 4. Okay. So this is less than, so we're going to use and. So that means -4 is less than or equal to x plus 3, which is less than or equal to 4. This is what our rule right here tells us. I'm going to go ahead and subtract 3 from both sides and the middle. That means -7 is less than or equal to x, which is less than or equal to 1. So why don't I go ahead and plot this? I've got where x is -7, -6, -5. Awesome. So my endpoints are included, right? I have from -7, all these possible values of x up until 1, which is also included. So that's going to give me a solution set of -7, 1. For this next example, I'm going to make this a positive so we can do an example with greater than. So I have the absolute value of x minus 1 is greater than 7. I can break this apart into its two inequalities. So I have x minus 1 is less than -7, and x minus 1 is greater than 7. That's a typo. Do I have the typo on the previous slide? I do. I'm going to go ahead and fix that. So here are my two inequalities. I get x is less than -6, and I get x is greater than 8. So we can go ahead and plot the solution. -6, -4, I'm counting by 2's. My solution set goes from -6 to positive infinity and from positive 8 to positive infinity. So I've got -8 infinity, comma -6, union 8, comma infinity. And there is our solution set.